Now let us consider another model here. Okay. When composite rod is free, composite length increases to 2.002 meters from temperature 20 to 120 degrees Celsius. When composite rod is fixed between the support, there is no change in composite length. Then Y and alpha of steel are, we are given alpha of copper as 1.6 in 10 to the power of minus 6 per degree Celsius, and Young's modulus of copper is given as 1.5 in 10 to the power of 13 Newton per meter square. The options are 0.3 in 10 power 13, 8 into 10 to the power of minus 6 per degree Celsius, 5 into 10 to the power of 13 and 10 into 10 to the power of minus 6 per degree Celsius, 7 into 10 to the power of 13, 12 into 10 to the power of minus 6 per degree Celsius, 9 into 10 to the power of 13, 14 into 10 to the power of minus 6 per degree Celsius. Okay. We are given a composite rod. In the diagram it is given like this. Total length of the rod is given as 2 meters, in which 0.5 is of copper and 1.5 is of steel. We know very well that alpha is equals to L2 minus L1 by L1 into T2 minus T1. This can be given as alpha equals to E by L delta theta. From this we can write as E equals to L alpha delta theta. Now the situation is of two different materials. So we can write it as E copper plus E steel is equals to L copper alpha copper plus L steel alpha steel into delta theta. The total expansion is given as 0.002 meters. It is equal to, here we are having length of copper is 0.5 into alpha of copper is given as 1.6 into 10 to the power of minus 6 plus length of steel is 1.5 into alpha of steel is not given to us, but increase in temperature delta theta is given as 120 minus 20, which is 100 degrees Celsius. On simplifying this, we get alpha of steel as 8 into 10 to the power of minus 6 per degree Celsius. Apart from this, what we are having is, after finding the alpha steel, okay, let us try to find the Young's modulus of steel. For that we are having thermal stress F by A is given as Y alpha delta theta. This can be written as F by A into delta theta is equals to Y alpha. In both the rods, the thermal stress per unit temperature remains constant. Therefore, I can write this as Y steel into alpha steel is equals to Y copper into alpha copper. As I know alpha steel, alpha copper and Y copper, I can find Y steel. Y steel equals to Yc into alpha C by alpha S. On substituting the values in the given formula, we can obtain the Y steel value as 0.3 into 10 to the power of 13 Newton per meter square. Therefore, our first option is correct. Now, in the previous problem, how to find the value of thermal stress? For that, let us try to understand regarding the total expansion of the composite rod. The total expansion of composite rod is given as ES plus EC is equals to F LS by A into Ys plus F into Lc by A into Yc. In this, when I take F by A common, I will get this as Ls by Ys plus Lc by Yc. Okay? And the value of expansion in steel is given as L S alpha S delta theta plus Lc alpha C delta theta. But I need the formula for thermal stress F by A. So, F by A is given as Ls alpha S plus Lc alpha C into delta theta divided by Ls by Ys plus Lc by Yc. Let us try to understand the variation of density of a solid with respect to the temperature. So, variation of solid with change in temperature. We know that gamma is equals to V2 minus V1 by V1 into T2 minus T1. But in general, density is equals to mass by volume, from which we can write as volume equals to mass by density. Using this relation, we are having V1 equals to m by d1 and V2 equals to m by d2. On substituting these values, we have gamma equals to m by d2 minus m by d1 divided by m by d1 into T2 minus T1. Now, gamma equals to m into d1 minus d2 by d1 d2 whole divided by m by d1 into T2 minus T1. M and m, d1 and d1 gets cancelled off. Remaining is gamma equals to d1 minus d2 by d2 into T2 minus T1. Now, let us say that T1 equals to 0 degrees Celsius, T2 equal to T degrees Celsius, then d1 becomes d0, d2 becomes dt. On substituting those values in this formula, we are having gamma equals to d0 minus dt by dt into t minus 0, from which we are having gamma equal to d0 minus dt by dt into t. So, therefore, d0 equals to dt into 1 plus gamma t, and dt is given as density at a given temperature, dt is given as d0 by 1 plus gamma t. When you take 1 plus gamma t into the numerator, we are having d0 into 1 plus gamma t whole to the power of minus 1. So, that dt is equals to d0 into 1 minus gamma t. So, when you want density at 0 degrees Celsius, we have the formula dt into 1 plus gamma t. At the same moment, when you want the density at temperature T, you have d0 into 1 minus gamma t as the formula. Now, let us have a model upon the previous formula which we have got, in which we say Density of gold is 19.3 gram per cubic centimeter at 20 degrees Celsius. Compute the density of gold at 90 degrees Celsius by adding steam to it, and we are given alpha equals to 14.2 into 10 to the power of minus 6 per degree Celsius. On completing the process, the options given are 18 gram per cubic centimeters, 18.5 gram per cubic centimeters, 19 gram per cubic centimeters, 19.24 gram per cubic centimeters. Now, in this case, what we do is alpha equals to d1 minus d2 by d2 into T2 minus T1, where d1 is density at low temperature and d2 is density at high temperature. In that case, alpha is given as 14.2 into 10 to the power of minus 6 equal to d1 is given as 19.3, and we have to find out d2 value divided by d2 into the change in temperature is given as 90 minus 20, which is 70, from which we can get d2 is equal to 19.3 divided by 1 plus 70 into 14.2 into 10 to the power of minus 6. On simplifying this part, we are having the value as 19.24 gram per centimeter cube. Let us try another model now. A sphere of coefficient of linear expansion alpha with mass m and radius r is spinning about an axis through its diameter with an angular velocity omega 1. If the temperature of the sphere increases by delta t, then its new angular velocity is, the options given are omega 2 equals to omega 1 into 1 minus 2 alpha delta, omega 2 is equal to 1 minus 2 alpha delta t, and omega 2 is equal to omega 1 into 1 plus 2 alpha delta t, and the last one is omega 2 is equals to omega 1 by 1 minus 2 alpha delta t. Fine. This is a model relating with angular momentum, okay, and the coefficient of linear expansion. We know very well that when there is no external torque, that is tau equals to 0, implies rate of change of angular momentum is 0, then in that case we are having angular momentum as constant, because there is no external torque in the given problem, only the temperature is increased. So, we are having angular momentum as constant one. So, we can write this as I omega equals to constant, so that I is proportional to 1 by omega. From fractional changes, we are having delta I by I equals to delta omega by omega with negative sign. Okay, fine. Now, for a given sphere, moment of inertia about a diameter is given as 2 by 5 mr square. As 2 by 5 is a constant, mb is also a constant, we are having I proportional to r square. So that delta I by I is equals to 2 into delta r by r. But delta r by r is given as alpha delta theta. On substituting, we have delta I by I equals to 2 alpha delta theta. Now, when you see the model here, delta I by I is given as minus delta omega by omega. On substituting this value here, we get delta omega by omega is equals to 2 alpha delta theta. From this we can write it as omega 2 minus omega 1 by omega 1 is equals to 2 alpha delta theta implies omega 2 minus omega 1 is equals to 2 alpha omega 1 delta theta. Bringing omega 1 this side, we get omega 2 is equals to omega 1 into 1 plus 2 alpha delta theta. Delta I by I is equals to 2 alpha delta theta, but delta I by I is given as minus delta omega by omega, so that minus delta omega by omega is equals to 2 alpha delta theta, and minus delta omega can be given as minus omega 2 plus 1 by omega 1 is equal to alpha delta theta, minus omega 2 plus omega 1 is equals to 2 alpha omega 1 delta theta. Omega 2 is given as omega 1 into 1 minus 2 alpha delta theta, which is our first option. Now let us try to understand another model, like a scale calibrated at a particular temperature will give correct reading only at that particular temperature. A correction is to be made to get exact measurement at any other temperature. Okay? If scale expands, correction to be made is positive, and if scale contracts, correction to be made is negative. Let us say a scale gives correct reading at T1 degrees Celsius and measurement is made at T2 degrees Celsius as L. Then the true reading is given as L dash is equals to L into 1 plus alpha delta theta. Here delta theta is taken as final temperature minus initial temperature. If T2 is greater than T1, then true reading is greater than the scale reading. Similarly, if T2 is less than T1, the true reading is less than the scale reading, and the correction to be made is plus or minus L alpha delta T. Okay? Now let us take a model upon the previous formula. Okay? A meter scale measures correct length at 0 degrees Celsius. Using this scale, length of an object is measured as 15 meters at 40 degrees Celsius. The correct length of the object is, and we are given alpha value as alpha equals to 20 into 10 to the power of minus 6 per degree Celsius. Okay? Fine. Now, the correction to be made is L alpha delta T. It is equals to 15 into 20 into 10 to the power of minus 6 into change in temperature is given as 40 degrees Celsius. So, we are having 15 into 8 into 10 to the power of minus 4 is equals to 120 into 10 to the power of minus 4 or 0.0120 meters. Now, initial temperature T1 equal to 0 degrees Celsius, final temperature is 40 degrees Celsius. So, actually what happens here is T1 is greater than T2 implies L dash is greater than L. So, L dash equals to L plus or minus L plus L alpha delta T, which is equals to 15 plus 0.0120. We are getting the result as 15.0120 meters. Now let us try to do another model on the same formula. A steel rod is found to be 1 meter long at 0 degrees Celsius when measured by brass scale, which is correct at 0 degrees Celsius. The length of steel rod as measured by the brass scale when both are at 100 degrees Celsius is, the options given are 99.1 centimeters, 90.90 centimeters, 100.8 centimeters, 99.92 centimeters. And we are given alpha S is equals to 11 into 10 to the power of minus 6 per degree Celsius. Alpha brass is equals to 19 into 10 to the power of minus 6 per degree Celsius. Okay, fine. Now, as the temperature is increased from 0 to 100 degrees Celsius, both the rods will expand. The expansion in steel rod delta Ls is given as Ls alpha s delta theta, and expansion in brass is given as Lb alpha b delta theta. Substituting the values in them, we are having 1 into alpha s is given as 11 into 10 to the power of minus 6. Change in temperature is given as 100. Similarly, 1 into 19 into 10 to the power of minus 6 into 100. Okay. From this, what we are going to get is 11 into 10 to the power of minus 4. Here 19 into 10 to the power of minus 4. Now, from this values, we understand that delta Lb is greater than delta Ls. Then difference in delta Lb to delta Ls is given as 19 minus 11 into 10 to the power of minus 4, which is given as 8 into 10 to the power of minus 4, and we obtain it as 0.008. Here alpha b is greater than alpha s, therefore the reading of the scale is equals to 1 meter minus 0.008, which we obtain it as 99.92 centimeters, which is our fourth option. Now let us have another model here. Two rods of lengths L1 and L2 are welded together to make a composite rod of length L1 plus L2. The coefficients of linear expansion of materials of the rods are alpha 1 and alpha 2. The effective coefficient of linear expansion of the rod is, we are given the options as L1 alpha 1 minus L2 alpha 2 by L1 plus L2, L1 alpha 1 plus L2 alpha 2 by L1 plus L2, square root of alpha 1 alpha 2 and alpha 1 plus alpha 2 by 2. Okay. Now, we are given that the two rods are welded. They are welded at this point. For example, they are having lengths L1 and L2, okay, and they are having coefficients of linear expansions as alpha 1 and alpha 2. Okay, fine. Now, we know that alpha is equals to L2 minus L1 by L1 into delta theta, change in temperature, that is. From this, we can write as alpha equals to delta L by L delta theta. Okay. So, this can be given as delta L is equals to L alpha delta theta. For rod number 1, we are having delta L1 is equal to L1 alpha 1 delta theta. For rod number 2, we are having delta L2 is equals to L2 alpha 2 delta theta. Now, total expansion is delta L is equals to delta L1 plus delta L2. Okay, but delta L is given as L alpha delta theta is equals to L1 alpha 1 delta theta plus L2 alpha 2 delta theta. Okay, fine. And now what we are having is L alpha equals to L1 alpha 1 plus L2 alpha 2, and alpha is given as L1 alpha 1 plus L2 alpha 2 by L, and that L is given as L1 alpha 1 plus L2 alpha 2 by L1 plus L2. So, the effective coefficient of linear expansion is given as alpha equals to L1 alpha 1 plus L2 alpha 2 by L1 plus L2, which is our second option. Now, let us try to have a model upon the previous formula. Okay. An iron rod of length 50 centimeters is joined to an aluminium rod of length 100 centimeters. All measurements refer to 20 degrees Celsius. The coefficients of linear expansion of iron rods and aluminium are 12 into 10 to the power of minus 6 per degree Celsius and 24 into 10 to the power of minus 6 per degree Celsius. The average coefficient of linear expansion, coefficient of composite system is, the options given are, first one 20 into 10 to the power of minus 6 per degree Celsius, 30 into 10 to the power of minus 6 per degree Celsius. Third one is 40 into 10 to the power of minus 6 per degree Celsius. And the fourth one is 50 into 10 to the power of minus 6 per degree Celsius. Here we are given length of iron rod is equals to 50 centimeters and length of aluminium rod is given as 100 centimeters. Let us say this is L1, this is L2, and alpha 1, alpha 2 values are also given. Alpha 1 is given as, for iron, alpha 1 is given as 12 into 10 to the power of minus 6 per degree Celsius, and alpha 2 for aluminium is given as 24 into 10 to the power of minus 6 per degree Celsius. According to the previous formula, we are having alpha is equals to L1 alpha 1 plus L2 alpha 2 by L1 plus L2. Okay. From this what we have got is 50 into 12 into 10 to the power of minus 6 plus 100 into 24 into 10 to the power of minus 6 divided by 50 plus 100, from which what we can get is 600 plus 2400 into 10 to the power of minus 6 divided by 150, from which we are going to get it as 3000 divided by 150 into 10 to the power of minus 6. So, zeros gets cancelled off here, and 15 20s we can say. So, 20 into 10 to the power of minus 6 per degree Celsius. So, we are having the result as the first option, which is 20 into 10 to the power of minus 6 per degree Celsius. A wire of length L0 is supplied heat to raise its temperature by T. If gamma is coefficient of volume expansion of the wire and Y is Young's modulus of the wire, then energy density stored in the wire is, we are given the options as half gamma square T square Y, and second option is given as 1 by 3 gamma square T square Y cube. Third option is 1 by 18 gamma square T square by Y, and the fourth option is 1 by 18 gamma square T square Y. Okay. The energy per unit volume for an elastic wire is given as E by V is equals to half into stress into strain. But here stress can be written as Y into strain. So, we are having energy density E by V equals to half into Y into strain, which can be written as half into Y into strain square. But strain equals to E by L, and E by L is given as alpha delta theta. Put alpha equals to gamma by 3. So, we are having E by L is equals to gamma by 3 into delta theta, and we know delta theta as T. So, E by L is given as gamma by 3 into T. On substituting, we are having E by V is equals to half into Y into gamma by 3 into T whole square, half into Y into gamma square into T square by 9. 9 2s are 18. So, we are having 1 by 18 into gamma square T square Y, which is our fourth option. Now, let us take another model here. Okay. The coefficient of linear expansion of an inhomogeneous rod changes linearly from alpha 1 to alpha 2 from one end to another end of the rod. The effective coefficient of linear expansion of the rod is, here we are having an inhomogeneous rod whose alpha value changes from one end to other end. One end is having the alpha value as alpha 1, other end is having alpha value as alpha 2. Gradually alpha 1 is changing from alpha 2 when we go from one end to another end. So, in such case, the effective coefficient of linear expansion of the rod is given as alpha equals to alpha 1 plus alpha 2 by 2. For example, let one end is having the linear expansion as alpha 1 equal to 11 into 10 to the power of minus 6 per degree Celsius, and other end is having alpha 2 as 18 into 10 to the power of minus 6 per degree Celsius. Then effective coefficient of linear expansion is given as alpha equals to alpha 1 plus alpha 2 by 2 implies 11 into 10 to the power of minus 6 plus 18 into 10 to the power of minus 6 by 2. So, that it is nothing but 29 into 10 to the power of minus 6 by 2. So, we are having 2 ones 2 and 2 fours 8, 14.5 into 10 to the power of minus 6 per degree Celsius. With the previous model, we have completed maximum number of models regarding the expansion of solids. Now, we are entering into expansion of liquids. In the liquids case, they do not have definite size and definite shape. As they do not have definite size and definite shape, they cannot be heated directly by putting them on the fire. So, liquids for heating purpose require a container for heating. Okay? So, when a liquid is poured into a container, it occupies the shape of the container. Okay? And next, liquids are having a definite volume. Okay? Fine. And next thing here is, to heat a liquid, first we have to heat the container. Whenever a container is heated at first, container expands. When container expands, liquid level comes down. Okay? And then the heat is continued, so the liquid expands and moves about the original level. So, liquids are having two expansions, one expansion which is seen by our eyes, other expansion the original expansion of the liquid. So, we are having two types of expansions in the case of liquids. They are real expansion and the apparent expansion. So, liquids are having two expansions. They are real expansion and apparent expansion. In the case of real expansion, we are having coefficient of real expansion. Denoted by the symbol gamma r, and it is defined as the real increase in the volume of liquid, real increase in the volume of liquid per unit volume for 1 degree Celsius rise in temperature is called coefficient of real expansion of liquids. It is given by the formula gamma r equals to real increase in volume delta Vr by initial volume V into change in temperature delta theta per degree Celsius. Next we are having coefficient of apparent expansion of liquids. Here what we say is the apparent increase in the volume per unit volume for 1 degree Celsius rise in temperature is called coefficient of apparent expansion of liquid. It is given as gamma A is equals to delta VA by V into delta theta per degree Celsius. Now let us try to obtain the relation between gamma R and gamma A. For that purpose, we consider a round bottomed flask having a marking up till A. Now let us try to fill the liquid up till the volume, up till this marking A, saying that volume as V. The liquid is at initial temperature T1 degree Celsius. Now by heating the container and along with the liquids, okay, we are increasing the temperature from T1 to T2 degree Celsius. So there is some rise in temperature. Let us imagine that the container is heated at first, then liquid is heated. When container is heated at first, the liquid level falls and the position is taken as B. And then liquid is heated so that the liquid level rises to C part. Let the neck region of the container is having area of cross section A. In the diagram, AB is taken as container expansion, AC is taken as apparent expansion, and BC is taken as real expansion. We know very well that length BC is exactly equals to length AB plus length AC. Multiplying area of cross section throughout, we have got BC into A is equals to AB into A plus AC into A. Now, BC into A is taken as real increase in volume delta VR and AB into A is taken as delta V, the container expansion, and AC into A is taken as delta VA. Divide throughout by V delta theta. Delta VR by V delta theta is equals to delta V by V delta theta plus delta VA by V delta theta. We know very well that delta VR by V delta theta is gamma R, delta V by V delta theta is gamma, delta VA by V delta theta is gamma A. So, gamma R equals to gamma A plus gamma. Just now we have seen the formula gamma R equals to gamma A plus gamma. In this case, gamma R is independent of container expansion. It does not depend upon the container expansion. Whereas, the coefficient of apparent expansion depends upon the container expansion. Gamma R cannot be 0 cannot be negative. Whereas gamma A can be 0, can be negative also. So, gamma A can be written as gamma R minus gamma. The first situation, let us say like this: if expansion of liquids is greater than expansion of the container, in that case gamma R is greater than gamma, so that gamma A will have positive value. Second thing, delta VR is equals to delta V, like the volume expansion of liquid is equals to the container expansion of the liquid. In that case, gamma R equals to gamma, which implies gamma A is having 0 value. Similarly, delta VR is less than delta V, in the sense the liquid expansion is less than the container expansion. In such case, gamma R is less than gamma, so that we are having gamma A is equals to negative value. So, gamma A can have positive value, 0 value and negative value. For determining the coefficient of apparent expansion of liquids, we use a formula gamma A equals to mass of liquid expelled, by remaining mass of liquids into change in temperature. This can be given as gamma A equals to m1 minus m2 into m2 into delta theta, where m1 is initial amount of liquid and m2 is remaining amount of liquid. When we subtract m2 from m1, we get mass of liquid expelled and m2 is remaining mass of liquid. So, we can find the value of gamma A. Let us consider percentage of change in volume of liquids. We know the formula as gamma R equals to delta VR by V into delta theta. This we can write as delta VR by V is equals to gamma R into delta theta. Multiply 100 on both sides, we get delta VR by V into 100 is equals to 100 gamma R delta theta. Therefore, the percentage of change in volume of liquid or the percentage of real increase in volume of liquid is given as 100 gamma R delta theta. Now, let us try to understand regarding the condition for constant volume of unoccupied space in the container at all temperatures. Okay? Let us consider a container having a liquid in it. Let volume of liquid is VL, volume of container is VC, and coefficient of real expansion of liquid is gamma R, coefficient of container expansion is gamma. Now, as the temperature of the container as well as the liquid is increased, the space unoccupied by the liquid is remaining constant, which means the expansion in the liquid is the same as expansion in the container. But we know very well that delta VL is given as VL gamma L into delta theta. Similarly, delta VC is given as VC gamma C into delta theta. Cancelling delta theta on both sides, we get VL gamma L is equals to VC gamma C. Now let us consider another case where same liquid is heated in two different containers. Let us say a container as P and a container as Q. Let P and Q are two containers. Okay. Now, the coefficient of real expansion remains same in both the containers. Gamma R remains same, whereas apparent expansion in first container is gamma AP and apparent expansion in the second container is gamma AQ. And gamma P is the container expansion, coefficient of container expansion. Gamma Q is the coefficient of second container expansion. Now, according to the formula, we are having gamma R equals to gamma AP plus gamma P, and here we are having gamma R equals to gamma AQ plus gamma Q. From the two equations, we are having gamma AP plus gamma P is equals to gamma AQ plus gamma Q. Further, it can be written as gamma AP plus 3 alpha P is equals to gamma AQ plus 3 alpha Q. Remember this formula for doing models on this one. Now let us try a model here. We are given in the problem like, if gamma R is to gamma A is equals to 4:1, then what is gamma A is to gamma? The options given are 3:1, 1:3, 4:1 and 1:4. Okay? We know the relation between coefficient of real expansion and coefficient of apparent expansion as gamma R equals to gamma A plus gamma, because we need the ratio between gamma A to gamma. We divide all the terms throughout by gamma A. What we are getting is gamma R by gamma A is equals to gamma A by gamma plus gamma by gamma A. Now, gamma R by gamma A is given as 4:1. I can write it as 4 equals to 1 plus gamma by gamma A. Bringing 1 this side, we get 4 minus 1 as 3. 3 equals to gamma by gamma A. And we can write this as gamma A by gamma equals to 1 by 3. Our option is second one. Now let us try another model here. If gamma A of liquid is 7/8 of gamma R of liquid, then alpha of vessel is. Here we are given gamma A equals to 7/8 times of gamma R. Now we know the formula, gamma R equals to gamma A plus gamma here. Substitute gamma A as 7/8 gamma R. So we can get it as 7/8 gamma R plus gamma. Then gamma equals to gamma R minus 7/8 gamma R, which is nothing but given as 8 gamma R minus 7 gamma R is gamma R by 8. Now put gamma equal to 3 alpha. So 3 alpha equal to gamma R by 8. Then alpha is given as gamma R by 24. Let us try another model. Okay. If gamma is coefficient of real expansion of a liquid, then temperature at which density of a liquid is 1% of its density at 0 degrees Celsius is. The options given are 99 by gamma, 1 by 99 gamma, 100 by gamma and 1 by 100 gamma. Okay. Now, as I have derived already in the previous case, we are having gamma r equals to d1 minus d2 by d2 into delta theta. From this we can write as d1 is equals to d2 into 1 plus gamma r delta theta. Let d1 is d0, d2 is dt, delta theta is t. In such case, we write this as d0 equal to dt into 1 plus gamma r delta theta. But in the problem it is given that density of liquid at a given temperature is 1% of density at 0 degrees Celsius. So, dt is given as 1%, that is 1 by 100 of d0. Substituting this value in dt, we are having d0 is equals to d0 by 100 into 1 plus gamma r delta theta. I can cancel d0 on both sides, so that I am having 100 equals to 1 plus gamma r delta theta. Okay? Bring 1 this side, we are having 100 minus 1 as 99, 99 equal to gamma r delta theta. So, here he is asking regarding the temperature part, therefore, delta theta is given as 99 by gamma r, which is our first option. A 1 liter flask contains some mercury. It is found that at a different temperature, the volume of air inside the flask remains same. The volume of mercury taken in the flask is, and we are given alpha C is equals to 9 into 10 to the power of minus 6 per degree Celsius, and gamma R equals to 1.8 into 10 to the power of minus 4 per degree Celsius. The options given are 150 ml, 750 ml, 100 ml and 700 ml. Okay, fine. Then, as earlier we have derived VL gamma L equals to VC gamma C. From this we are having VL is equals to VC gamma C into VC gamma C divided by gamma L. Okay, now volume of container is given as 1 liter. 1 liter I can write as 1000 ml, and gamma value of container is 3 alpha C. 3 alpha C is 3 nines are 27. 27 into 10 to the power of minus 6 divided by gamma L. Gamma L of liquid is given as 1.8 into 10 to the power of minus 4. Okay. Then cancelling 10 power minus 4 with 10 power minus 6, we remain with 10 power minus 2. 10 power minus 2 cancel off with 2 zeros. Then we are having 270 by 1.8 or 2700 by 18, we are having 9 twos are, then we are having 9 300s are. Okay. 300 by 2 will give us 150 ml, which is our first option. Now let us try another model here. A weight thermometer contains 52 grams of a liquid at 10 degrees Celsius. When it is heated to 110 degrees Celsius, 2 grams of the liquid is expelled. The coefficient of real expansion of liquid is, we are given alpha equals to 9 into 10 to the power of minus 6 per degree Celsius. As we know alpha, from which we can find gamma of container, okay, and now if we find coefficient of apparent expansion, then by adding gamma A with gamma, we can find gamma R. That is the required thing in the problem. Okay. At first, we try to find out gamma value. Gamma is given as 3 alpha, 3 into 9 into 10 to the power of minus 6, which is given as 27 into 10 to the power of minus 6 per degree Celsius. And the next thing is regarding gamma A. Gamma A equal to liquid expelled by remaining liquid into change in temperature. And in the problem we are given liquid expelled as 2 grams and remaining liquid is from total 52, we have to subtract 2, so we are going to get 50, and change in temperature is given as, from 110 if you subtract 10 you are having 100. So that we get the value as 1 by 25 into 10 to the power of minus 2, and 1 by 25 is 0.04 into 10 to the power of minus 2, which can be given as 4 into 10 to the power of minus 4, and gamma r equals to gamma a plus gamma. So, gamma a is given as 4 into 10 to the power of minus 4, whereas gamma is given as 0.27 into 10 to the power of minus 4. On adding we get 4.27 into 10 to the power of minus 4 per degree Celsius. Let us try another model now. A wooden block of density 860 kg per meter cube at 0 degrees Celsius is floating on benzene liquid of density 900 kg per meter cube at 0 degrees Celsius. The temperature at which the block just submerged in benzene is gamma wood is given as 8 into 10 to the power of minus 5 per degree Celsius. Gamma of benzene is given as 12 into 10 to the power of minus 4 per degree Celsius. Now, let us try to understand regarding the submerge of the wooden block. Imagine the container having a benzene in this manner, and the wooden block is just floating on the benzene liquid at a temperature 0 degrees Celsius. When the temperature is increased to some T degrees Celsius, the wooden block just submerges and comes to the ground and comes to the bottom surface of the liquid, okay, just submerges, okay, and it is just looked like a suspended body. In such case, from law of flotation we are having V1 D1 equals to V2 D2, okay. When the body is just suspended, we can write it as V D1 equals to V D2. So, V gets cancelled off. Here density of wood at T degrees Celsius is equals to density of benzene at T degrees Celsius. Now, dW T degrees Celsius can be written as D naught dW 0 by 1 plus gamma Wt is equals to dB at 0 by 1 plus gamma B by T. Let us substitute the values in this expression. So, we get density of wood, it is given as 860 divided by 1 plus gamma of wood is given as 8 into 10 to the power of minus 5 into the temperature equal to, and the density of benzene is given as 900 by 1 plus 12 into 10 to the power of minus 4 T. On simplifying this equation, we are getting T is equal to 42 degree Celsius.